In 1995, finalizing a single frame of computer animation for a feature film took roughly 7 hours of processing time. The hardware available in the mid-90s was heavily restricted, and consumer computing power is exponentially faster today than it was back then. But if you look at a modern, high-end television production today, rendering a single frame of those highly detailed dragons still takes exactly the same amount of time, roughly 7 hours. Generative video models are promising to bypass this historical bottleneck. They offer the ability to type a prompt and watch a highly detailed cinematic scene assemble itself in mere seconds. A speed increase of that magnitude naturally raises the question of whether traditional digital artists are about to lose their jobs. But that massive leap in efficiency hides a critical flaw in how these algorithms actually construct an image. High-end filmmaking rarely involves generating a random, aesthetically pleasing image. It requires executing a director's highly specific, rigid vision. To see where the technology actually stands, we can run a stress test. We start with real-world drone footage of a specific, rushing Icelandic waterfall, and the goal is to seamlessly insert a massive fantasy creature into the environment. The scene comes with strict physical rules. The creature has to displace the heavy flow of the water, and the digital camera movement must perfectly lock on to the drone's reverse flight path. By putting a human digital artist and a machine-driven AI in a head-to-head trial, we can see exactly which system has the ability to obey these strict constraints. Let's look at why the human approach takes so long. A traditional digital artist has to manually build physical interactions from scratch. This diagram shows the sheer complexity of fluid dynamics. The software calculates the gravity and density for thousands of individual droplets as they collide with a moving object, forcing the computer to simulate true physical mass displacement. Then comes the light simulation, known as ray tracing. The computer maps out how millions of individual beams of light bounce off the water, the creature, and the surrounding environment to create accurate shadows and reflections. This intense mathematical workload is precisely why render times remain incredibly high. By the 2010s, films pushing this physical lighting technique could take up to 29 hours to process a single frame. You are trading massive amounts of computational time in exchange for absolute physical accuracy and total creative control over the final result. The AI approach operates completely differently. It bypasses all of those physics, geometry, and lighting calculations. This animation illustrates how the neural network operates. Having been trained on millions of videos, it is statistically guessing what the pixel should look like based on your text prompt. But when forced to apply that guessing game to the creator's real-world Iceland footage, it falls apart. The system struggles to integrate the creature into the rigid spatial constraints of the actual location. The scale of the creature changes wildly from frame to frame, the water interaction lacks physical logic, and the algorithm even hallucinates a completely different person over the creator's green screen footage. This reveals the core vulnerability of generative video. When you demand exact adherence to a human director's strict visual constraints, an algorithm designed to guess the next pixel simply cannot comply. The true capability of the AI only appears when you remove the restrictions. In a final test, the developers abandoned the drone footage entirely and fed the system a pure text-to-video prompt. The result is breathtaking. Free from matching a real location, it produces a sweeping, structurally sound, and cinematically perfect sequence generated entirely from scratch. We are looking at two entirely different tools. Traditional digital art is a precision instrument designed to execute a singular, uncompromised human vision. Generative video operates as a chaotic co-creator. It produces its most stunning work only when you surrender control of the details and let the machine make the creative decisions. Because of this control gap, hyper-specific, world-building cinema will continue to rely on traditional, pixel-by-pixel rendering pipelines to ensure every detail matches the script flawlessly. Algorithmic generation won't replace traditional digital artists anytime soon. Instead, it is spawning an entirely new medium, one where